Hey guys, Mr. Palmer here with a review or a little intro to buffers and titration curves. This is a really important idea in advanced placement chemistry. For many people, this is a struggle for them to understand it. You got to spend some time on it, and I think if you kind of go through it step by step and take it as in an organized way, these problems become a lot simpler when you start to realize how you can tackle them. I started this video off with a little diagram. This is a typical graph you might see of a titration of a weak base, or sorry, a weak acid by a strong base. And pretty much whenever we're mixing acids and bases together, we can think of it as a titration, right? We're going to be adding some amount of our base to our acid or some amount of acid to our base. And this is the graph you produce with a weak base or a weak acid and a strong base, this curve, and we'll talk about the calculations that generate that curve. But we can pretty much think about this anywhere on this line as being some amount of acid and some amount of base mixed together. And we'll talk about those amounts and be able to calculate the pH at any point, that is, at any ratio of mixtures of acid to base in a problem. So what's really important to understand is that in these weak acid titrations, the equilibrium that we have going on is for a weak acid, right? The weak acid turning into its conjugate base. This is this first equilibrium I have set up here. This is our generic expression for some weak acid, HA, dissolved in water. It's going to go through hydrolysis, which means reacting with water, to form our hydronium and our conjugate. So whenever we have a buffered solution, or wherever you have a solution where we're doing this titration, we wind up with some amount of the weak acid and some amount of its conjugate base. Well, remember, the conjugate base, it can also interact with water. It does its own hydrolysis, and it is going to produce the hydroxide, and it's going to turn back into our acid in water. So this is the equilibrium that really causes this titration curve and this buffering capacity of a solution. So when we talk about a buffer, we're saying it's a solution that contains a weak acid and its conjugate base, or a weak base and its conjugate acid. It resists changes from the addition of strong acid or strong base because of the Le Chatelier principle. So if I have a solution that contains a weak acid, right, we know it also has conjugate base. So that is, if I have a container that's a buffer, right, I'm going to have my acid, and it's going to be in equilibrium with its conjugate, right? And by adding strong base, right, that's hydroxide, you can convert the acid into its conjugate. If you have a strong acid and you add it to this solution, you're going to be converting the conjugate base into its acid. So what's going to happen is whether you're adding a strong base or whether you're adding a strong acid to a buffer solution, the solution is going to adjust to maintain its pH. That is, it's going to resist changes by neutralizing the base with acid or neutralizing the acid with base. And we can use stoichiometry to sort of figure that out. The equation that we use for this is called the Henderson-Hasselbach equation. And it's derived by looking at our acid equilibrium expression, right, which is right here. This is our generic form, again, with the product, the conjugate base on top, and our weak acid on the bottom. If we take the negative log of both sides of this equation, we get some special things, right? The negative log of Ka is called the pKa, right? And so every acid has a unique pKa value, which you can calculate from its Ka. That's going to be equal to the pH minus the log of this factor. Or the way we write it in the typically is to say that the pH of a solution for a weak acid can be calculated by taking the pKa value and adding this factor. So this is just an algebraic rearrangement of this third equation. The log of this factor, and that's coming from this guy up here. We're taking the log of this part of our equation, right? this part of our equation right here, the negative log of the hydronium, was our pH. This factor is coming down, right, as the negative log. So down here at the bottom, we can see that if I have a buffered solution, the pH is going to be equal to the pKa plus some factor. Now, if we look at this factor, if this factor has a larger numerator, right, if we have more of our base, we're going to get a bigger number up here when we take the log of it, and that means it's going to be a pH that's a little higher than the pKa. If I have a bigger denominator, that means if I have more of my acid, less of my base, I'm going to get a number that's less than 1, and when I take the log, I'm going to get a negative number. So it's going to be a pH that's a little less than the pKa value. Okay, well, what does this look like? So when we do these titration curves, we have this classic kind of graph, right? So here is a weak acid being titrated with a strong base. Let's pretend that this is, let's say, 0.1 molar weak acid plus 0.1 molar OH minus being added to it, right? And we look, well, what are the points we can identify? The initial, well, why is it here and not down here at 1? Well, that's because it's a weak acid. A 0.1 molar weak acid is not going to be down here with a pH of 1 because it's weak. It's going to be something higher than that, right? More basic. The equivalence point, remember, where the moles of acid equal the moles of base, right? It looks like this happens at 30 mils. And if we go across over here, you see that that equivalence point happens. Where does it happen? It's happening somewhere above 7, right? If you're having a weak acid and a strong base, that pH is going to wind up being above 7. If we contrast this with a strong acid, right? What would a strong acid look like? A strong acid is going to start out down here, and it has an equivalence point that's going to happen, same volume, but it's going to be down at 7. Okay, so its curve doesn't look like this. It's going to start down here, stay low, 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 rapidly increase to the equivalence point, and then you'll see from that point on it merges and becomes the same as the weak acid one. They're identical after we reach the equivalence point. But we see that there's no buffering region here. For a weak acid, though, we have this buffer region. Okay. And in the buffer region, we have this equilibrium going on. We have the acid and we have the base, and they are in equilibrium with one another. So we're going to do some problems with this. What points are we going to look at? So in this titration curve, some very important points we're going to look at. First of all, we're going to look at the interinitial part where we've added no base. We are going to look at the equivalence point, which is at the inflection point of our curve. We are going to look at the half equivalence point. So wherever our equivalence point is, if we go to half that volume, right? And those are the 3 special points that we're going to look at. But we can actually find the pH at any point along this line using the Henderson-Hasselbach equation, right? We can use this equation to solve using this extra little tidbit here when we look at the concentration of the conjugate and the concentration of our acid. Okay, so I'm going to pause there. I'm going to hop back into this and talk about some of the unique places and how we go about calculating them on this graph. And that'll be back in our first part of doing our calculations.